A very good morning all of you. In the last lecture we have seen how to design the synchronous counters using T flip-flop. We have seen up counter and down counter. We have used excitation table to construct to design the synchronous counters. So in today's lecture we are going to see how to design the up down counter using the single circuit, as well as we are going to see how to design the counters with JK flip-flop or either up counter or down counter, and later we are going to see how to design the modulus counter depending on our requirements. So let's start with a recap of yesterday's class. So in the last class we have seen up counter using T flip-flop. So in this case your first flip-flop always connected to 1 in both the cases, whether up counter or down counter, whereas your second flip-flop output your Q is connected to, T1 input. In this case your Q bar is connected as a T1 input. This is your Q and this is your Q bar. Now this is my Q1 and this is my Q0. Similarly here also Q0 and Q1. Now these two circuits, this circuit will have the same, the clock is given simultaneous to both the flip-flop at the same time. Now this circuit is counting upward direction, that is 0, 1, 2, 3 and 0. This is counting downwards direction 0, 3, 2, 1, 0, 3. Now I am going to add these two circuits, make a single circuit so that we don't have to use separate circuit for up counting or down counting. So I am going to add extra control inputs so that we can select depending on our requirements. Let's see how to do the up down counter using the same circuit. I am not going to follow all the design rules. I am directly taking, as we already know the logic from the previous lectures. So let's take two flip-flop as usual. This is my T0 and this is my T1. Now let's take Q output from here and Q0, your Q0 and Q0 bar. Let's give it to an AND gate, here also AND gate. Now connect with an OR gate, output of these two AND gates. Now this OR gate output you give it as a input to the second flip-flop T1. Now add one extra control. This control line will decide whether you are going to do the up counting or down counting. The same circuit we already seen in synchronous case also. So let's make it a NOT gate here. Now let's say this is gate 1 and this is gate 2. Now clock is given as usual. So this is my Q0 and this is my Q1. This is my control M. If you look at here, if M equals 0, if M is 0, very clear, the 0 goes here. That means G1 will be disabled and this 0 becomes 1 here. This 1 enable the G2. When G2 is enabled, your Q0 bar will pass through this AND gate and pass through this OR gate, will act as input to the second T flip-flop. So that means it is going to count in the downwards direction, that is 0, 3, 2, 1, so on. Similarly, if M equals 1, in this case your G1 will activate or enable, your G2 will be deactivate. In this case your G1 will activate, your Q0 bar will pass through this AND gate and pass through this OR gate, act as input to the second flip-flop. In this case it is going to count in the up direction, that means 0, 1, 2, 3 and so on. So the same logic can be extended to 3-bit, 4-bit. Only thing is, for every in between the two flip-flops you have to add two AND gates and the two AND gates will be connected to the common control line. And this AND gate output will be added with the OR gate. The OR gate output will act as the input to the second T flip-flop. So this is how we can design both up counter and down counter. Now I am going to show you the simulation of the same circuit to check whether it is counting properly or not. Now let us simulate the same circuit. If you look at here, the same circuit we have designed, two T flip-flops. It is actually JK flip-flop. I shorted both J and K, so it will act as a T flip-flop. And you can see the Q is connected to one AND gate and Q bar is connected to another AND gate. This AND gate second input is connected to the common control line through a NOT gate here and then directly to the upper AND gate. Then output of these two AND gates are connected to the OR gate. This OR gate output is connected as a input to the second T flip-flop. Now we'll try to run the simulation and see how it is going to count upwards and downwards direction. So let's clear it. If you look at here, my control is 0, that means your 0 goes here and enable the lower AND gate, that means your Q bar is going to act as an input to the second flip, that means it's going to count in the downwards direction. The moment I keep my clear equals to, it's going to count in the downward direction. 2 1 3 2 1 0. If I keep my control to 1, it's going to count in the upward direction. Let's make it. Now you can see 1 2 3 0 1 2 3 0. So that's how you can, now it's going to count the downward direction. Now upward direction. This is how you can design the circuit for up down counting. This can be extended to 3-bit and 4-bit by applying the same logic. So now let us design the 2-bit up counter using JK flip-flop. So till now we have seen how to design the synchronous counter using T flip-flop. Now we are going to see with the JK flip-flops. So as usual we follow the step number 1. You require 2 flip-flops to store the 2 bits or to count from 0 to 3, that means 0 0 0 1 1 0 1 1, that means you require one flip-flop for storing first bit and second flip-flop for the second bit. Now go to the step number 2. In step number 2 we are supposed to make the state diagram. It's very clear. You start from 0, then goes to 1 1 to 2, then 2 to 3 and 3 to 0. This is my state diagram. If you represent in the binary representation, it starts with 0 0, then goes to 0 1, then goes to 1 0, then goes to 1 1, from there it goes to 0. So this is my state diagram. So in step number 3 I am going to construct state table. So based on the state diagram, so present state, next state, so this Q0, Q1, Q0 star and Q1 star. So if both are 0 0, it goes to 0 1 state. If it is 0 1, goes to 1 0 state. If it is 1 0, it goes to 1 1 state. If both are 1 1, it goes to 0 0 state. This is my state table. Now step number 4, I am going to select JK flip-flop as we need to do with JK flip-flop. Now step number 5, correct excitation table. So I am going to use the same state table to make the excitation table by extending the table. So required JK inputs. So in this case you are supposed to have total 4 because J0, K0 and J1 and K1. Let's see. So this is J1 and K1 and J0 and K0. We need to find out what are the J and K values for Q0 transition, what are the J1 and K1 values for the Q1 transition also. So if you look at here, now let us fill the excitation table. So if you look at here, your Q0 is changing from 0 to 1. 0 to 1 transition require 1 comma x. If you remember the JK flip-flop excitation table, J, if you remember the JK flip-flop excitation table, 0 to 0, 0 comma x, 0 to 1, 1 comma x, 1 to 0, x comma 1, 1 to 1, x comma 0. So first one is 0 to 1, that means 1 comma x. Next is 1 to 0. 1 to 0 is x comma 1. Then 0 to 1, 1 comma x. Then 1 to 0, x comma 1. So these are the inputs you are supposed to give to make Q0 transition. Similarly, if you look at for J1 and K1, 0 to 0, 0 comma x, 0 to 1, 1 comma x, 1 to 1, x comma 0, 1 to 0, x comma 1. Now we need to make the 4 KMFs, 1 KMF for J0, 1 KMF for K0, 1 KMF for K1 and J1. We will try to make the KMFs and we will try to see. So let's start with J0. So you are supposed to make, this is my Q1 bar, Q1 and Q0 bar and Q0. So if you fill your J0 1x, 1x, so I can take this as a quad. J0 is 1. Similarly, if you take K0, same thing, x1, x1, again I can take this entire thing as a quad, so I can make K0 also 1. Now let us do it for K1, J1. Then 0, 1, x and x, so I can make this as a pair, so it will be Q0. If I do it for K1, x, x, 0, 1, I can form this as a pair. In this case K1 also Q0. Now we know what inputs I am supposed to give for first JK flip-flop and what inputs I am supposed to give for the second JK flip-flop. Now I can construct my circuit for the upcounting using JK flip-flop. Now let us construct the circuit. This is my JK flip-flop 0 and this is my second flip-flop, that is JK flip-flop 1. So as for the K-map simplification, we got J0 should be connected to 1 and K0 connected to 1 always, and your J1 should be connected to Q and your K1 also connected to Q. Now the clock is given as usual, same. This is my Q0 output and this is my Q1 output. Now this circuit is going to count from 0, 1, 2, 3 and so on. If you want to, this is up counting. If you want to do it for a down counting, if you do all the procedure same, what you are going to get it, you are going to get the same thing except instead of Q0 acting as an input for the second flip-flop, if Q0 bar will act as an input for the second flip-flop. So when Q0 acts as an input for second flip-flop, it is going to count in the downwards direction. That means 0, 3, 2, 1, 0 and so on. Okay. Now we'll try to construct the same circuit and we'll try to verify whether our circuit is correct or not. Let us simulate the counter circuit. Now let us simulate the counting circuit with the JK flip-flop. It is actually equivalent to a T flip-flop. Only thing is we derived separate expression for J0, K0 and J1 and K1. you look at here, my J0 is connected to 1 and K0 also connected to 1, and my J1 is connected to Q and K1 also connected to Q, and rest all are same. Clock is given as usual and preset clear, and these are my outputs. Let's run the simulation. Let's make it clear. Now you can clearly see 3, 1, 2, 3, 0. So my circuit is counting in the upward direction. If I want to make it downwards, then just need to change my input to the second flip-flop to Q bar, then it will count in the downwards direction. This is how we can construct both up counter and down counter using. So we have designed up counter and down counter in the last lecture. Now we'll try to design the up down counter by following the same set of rules. Now we are going to see how to design up down counter using T flip-flops, which can count from 0 to 3 or 3 to 0. That means up counting and down counting at the same place. So now we'll try to start our design procedure. Step number 1, you require 2 flip-flops minimum to count 0 to 3 or 3 to 0. And step number 2, you have to make the state diagram. In state diagram, we have two constraints now, because we need to count in the upward direction, downward direction. So we have to assume an extra control input. That control I am considering as M. If M equals 0 and M equals 1, so I am assuming when M equals 0, I am supposed to count in the downwards direction. You can assume other way around also. If M equals 1, I am supposed to count in the upward direction. In this case, I am going to write it as 0 to 1, sorry, 0 to 3 and 3 to 2, 2 to 1 and 1 to 0, or else 0 0 to 1 1, 1 1 to 1 0, 1 0 to 0 1, then 0 0. This is my Q0, this is my Q1 when M equals 0. When M equals 1, I am planning to count in the upward direction. That means 0, 1, then 2, then 3 and 0. So in the same way, 0 0, 0 1, 1 0, 1 1 and 0 0. Now I am going to make the state table by using the state diagram. So present state and this is the next state. Please remember, we are going to have an extra control this time along with Q0 and Q1. So if M equals 0, so I will take the first 4 input combination of 0 0, 0 1, 1 0, 1 1. For this I am taking M equals 0. When M equals 0, I already defined M equals 0 is supposed to count in the downwards direction. So that means 0 0 goes to 1 1 and 0 1 goes to 0 0, 1 0 goes to 0 1, 1 1 goes to 1 0. So this is a downwards part, this is a down counting part. When M equals to 1, again I am going to consider 0 0, 0 1, 1 0, 1 1. So same 1, 1 and 1. So in this case 0 0 will goes to 0 1 state, 0 1 goes to 1 0 state, 1 0 goes to 1 1 state, 1 1 goes to 0 0 state. Now these are the 3 inputs now. This will act as a 3 inputs. And this is my next state, this is my Q0, this is my Q1. So now you need to select the flip-flop, that is step number 4. Since I already decided want to use T flip-flop, I am going to use T flip-flop. Now step number 5, I am going to design the excitation table by considering Q0, Q1 transitions with control. Okay, so if you write it here, required T inputs, this is my T0 and this is my T1. So if you look at here, the first case 0 to 1, 1 to 0, 0 to 1 and 1 to 0. That means you need T01 for all the 4 states, because it is toggling for all the 4 transitions. If you look at the T1, so if you look at your Q1 transition, 0 to 1 requires 1 and 0 to 0 requires 0 and 1 to 0 requires 1 and 1 to 1 requires 0. So this is for the up counting. Now if you look at this is for down counting. Now look at the up counting. Again your 0 to 1 transition requires 1, 1 to 0 1, 0 to 1 1 and 1 to 0 1. If you look at this 0 to 0, so these 4 are done. Now we look at it from here. If you look at it, 0 to 0 0, 0 to 1 1, 1 to 1 0, 1 to 0 1. Now you got the T1 required inputs for T0, required inputs for T1. Now we need to make a K-map for T0, K-map for T1 by considering Q1, Q0 and M as a input. So I need to make a 3 variable K-map for T0. So let's make 3 variable K-map for T0. So this is my M bar, this is my M, this is my Q1 and Q0 bar, Q1 in. Now if you fill your T0 outputs, all are ones. So in this case your T0 becomes 1 for all the transitions, whether it's going to be up counting or down counting. Similarly, if you make it for T1, if you make it for T1, it is 1 1 0 1 0 1 0 0 1 0 1 and 0 1. Now you can form this as a pair and this as a pair. So if you write the T1 expression, for this I can write it as M into Q0 plus this M into Q0 plus M bar into Q0 bar. If you look at T0 always connected to be 1 and T1 is connected to M into Q0 plus M bar into Q0 bar. That means you are supposed to connect your M to Q0 and this is your Q0. Similarly, this is my Q0 bar and this I am supposed to connect through a NOT gate. Now this I am going to use an OR gate. This output I am supposed to give it to the T1. So, okay. I will try to implement the circuit by using the same logic, and we'll try to see whether you are going to count both upwards and downwards as per our requirement. So that means your final circuit will be first T flip-flop. This is always connected to 1 T0 and this is your second flip-flop. And second flip-flop will be connected through a AND gate here, through a one more AND gate here. This AND gate is connected to a control input through a NOT gate here, and it goes here and connect here. This will pass through an OR gate and this will act as an input to the second flip-flop T1. This is my Q1, this is my Q0. Now we are going to implement the same circuit using DIT software, and this is the clock which will be given simultaneously to the both the flip-flops. Now we'll try to verify this working. This is my control M. Now you can see here, this is my up down counter, whatever we derived till now. If you look at here, my J0 and K0 connected one permanently. If you look at here, my T is connected to one permanently, my T1 is connected through a OR gate through another two AND gates, and these two AND gates are controlled by a control input M. If M equals 0, it's going to count in the downwards direction. If M equals 1, it's going to count in the upward direction. Now we'll verify. If M equals 1, this upper gate will be enabled. If M equals 0, this lower AND gate will be enabled. We'll try to verify. So let's clear it. Now M equals 1. I am making M equals 1. When M equals 1, this upper one will be enabled. That means Q act as input to the second T flip-flop. So as a result, you are going to count in the upward direction. Now we'll see. 1, 2, 3, 0. So it is counting in the upward direction. If I make my control input to 0, it's going to count in the downward direction. Now you can see 0, 3, 2, 1, 0, 0, again 3, 2, 1, 0, 0. So this is how we can design the circuit for up-down counting by using the same procedure. We can extend it to 3-bit and 4-bit by using the same logic. We don't need to derive it once again. You can just extend the same logic for the next flip-flops also. So now let us design the modulus counters. Like what we did it in the asynchronous case. So let's take example of mod 6 counter and mod 10 counter. Mod 6 means it should count from 0 to 5. Mod 10 means it should count from 0 to 9. There are two ways we can do it. We can construct the modulus counters. One is direct logic, where whenever required state is reached, output sets to 0, 0 by extra circuit. And the second case is a design procedure. In this case, unwanted state inputs and the respective outputs consider as 0. So that means whenever the circuit encounters an unwanted state, that output will immediately goes to all 0, 0 state. We'll check one by one how this is going to work. So we'll first see the direct logic. So let's take the mod 6 counter. So what we can do is we can take 3-bit up counter which can count from 0 to 7. We can modify the circuit of 3-bit up counter so that it can count only 0 to 5. We'll see how to do that in a moment. Let's take the 3-bit up counter using this T flip-flop. As you already know, T0 always connected to 1, T1 is always connected to Q0, and your T2 is connected through a AND gate. Say Q1 and this is your Q2. Now clock is given as usual. This is a 3-bit up counter which can count from 0 to 7. This is my Q0, Q1 and Q2. Now let's take, if you write in the binary combination, first all zeros, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 0 0 1 0 1. Now since we need to design only till mod 6 counter, that means 1 2 3 4 5 and 6. So there are 6 states, that means mod 6 are reached. So in the next clock cycle it goes to 110 momentarily. So it goes to momentarily. What I am going to do, I am going to connect these two, that means your Q0, Q1 and Q2. So I am going to connect to a NAND gate your Q1 and Q2, so that whenever Q1 and Q2 becomes 1, it is going to produce a 0. This 0 I am going to apply as a clear input to all the 3 flip-flops. So it is going to clear all the flip-flops to 0 0. That means this state will be there only a momentary. This will be fraction of nanoseconds will be there. Then it immediately goes to all 0 states. Similarly, if it encounter 110 also, 111 also, same again. Your 11 is going to produce a output 0. This will be applied a clear input to the all the flip-flops. Again it goes to all 0 0 states. Okay. So this is for 0 to 5. Suppose if you want to count from 0 to 10, that means mod 10 counter. In case of mod 10 counter, we can use 4-bit up counter. So in case of 4-bit up counter, it starts from all zeros, Q0 to Q1, Q2 and Q3, and it goes till 1 0 0 1. This is 9. That means 0 to 9 total 10 states. When 10 states is reached, in the next clock it goes to 1 0 1 0 state momentarily for a fraction of nanoseconds. Now I am going to take these two inputs as a input to the NAND gate. That means I am going to use one NAND gate here. For this NAND gate I am going to connect my Q3 and Q1. Whenever Q3 and Q1 is 1 1, it is going to produce output 0. This output I am going to use as a clear input to all the 4 flip-flops. So it is going to set the count to all zeros. This will take in a momentary action. This you don't even observe that counter is going to 1 0 1 0 state. It directly goes from 1 to all zeros. Now we will verify these two logic. This is a direct logic by directly resetting your counter wherever we required. Now you can see here this is the same circuit which we use for the up counting. The only extra thing I added here is this extra NAND gate. If you observe clearly, for mod 5, for mod 6 we need to count till. So this is a circuit. This is same as your up counting circuit which can count from 0 to 7. Now we need to count only 0 to 5. That means whenever 6 encounter, 6 means 1 1 0. That means this is 1, this is 1 and this is 0. Now if you observe carefully, this NAND gate input is Q1 and Q2. So this is your Q1 and this is your Q2. Whenever Q1 and Q2 are 1, then going to produce 0. This 0 will pass through this AND gate and will apply as a clear input to the all the flip-flops. It's going to clear to all zeros. Let's run the simulation and let's see. Now I cleared all the flip-flops. Now we are going to make clear equals to 1. The moment I make clear equals to 1, it's going to count 0 to 5. The moment it reaches 5, it goes to 0 state. Let's see. 1 2 3 4 5, then 0. So moment it goes to 6 state, and when it reaches 6 state, this NAND gate going to produce a 0, and this 0 will pass through this AND gate and will apply as an input to all the 3 flip-flops. This is going to clear all the outputs to 0 0. This is for mod 6 counter which can count from 0 to 5, synchronous mode. Similarly, we will see mod 10 counter which can count from 0 to 9. So in this case, I connected my Q3 and Q1 as input to the NAND gate. That means 1 0 1 0. So whenever 1 0 1 0 is encountered, that is 10, your NAND gate going to produce a 0 here. This 0 will be applied to all the flip-flops to clear it. Let's clear the flip-flop outputs to 0. Now we'll see whether it's going to count 0 to 9 or not. 1 2 3 4 5 9, then 0. So you can clearly see it is counting only 0 to 9, because the moment it reaches 1 0 1 0, this NAND gate will produce a low pulse. That low pulse will clear all the flip-flops to 0 0 state. So this is how we can directly design a modulus counters in synchronous design also. Now we'll see how to do it in a proper stepwise designing. Now we'll see the second logic or second way of doing the modulus counters. Using the standard procedure. So let me take a simple example of mod 6 counter. So that means it should count from 0 to 5. So 6 and 7 are invalid. We should not see in the output side. So we'll follow the same step. Step number 1. To design 0 to 5, we need at least 3 flip-flops. Step number 2. State table. Step number 2, state diagram. So here we are supposed to take care very much. So it starts from 0, then goes to 1, 2, 3, 4, then 5, it goes to 0. If 6 comes, it's supposed to goes to 0. If 7 comes, it's supposed to goes to 0. Please remember this, very important. So the same thing if you write in a binary form, it starts with all zeros, then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, then 0. If at all if it comes 1 1 0 or 1 1 1, it's supposed to go to the 0 0, that means reset state. If the flip-flops encounter this input combination, it's supposed to goes to the 0 0. Now we'll try to make the state table, it will be more clear. The present state and next state, Q0, Q1 and Q2, Q0 star, Q1 star and Q2 star. If it is 0 0, it goes to 0 0 1 state. If it is 0 0 1 state, it goes to 0 1 0. If it is 0 1 0, it goes to 0 1 1. If it is 0 1 1 state, it goes to 1 0 0 state. If it is 1 0 0 state, it goes to 1 0 1 state. If it is 1 0 1 state, it's supposed to. Now here is the interesting point. Whenever it encounter 5, next state supposed to be 0 0. We are not making it to 6 transition this time. See, in the first design we said that the counter momentarily goes to 1 1 0, then it resets to all zeros. But in this case we are directly making it 5 to 0 0. Similarly, when it encounters 1 1 0 also, we are making them to go to all zeros. Similarly, if it all ones comes also, we are asking the counter to go to all 0 states. So this is a state table. It's very important. If you understand, then it is easy to design any type of modulus counter. Now I'm going to extend this to make my excitation table. So step number 4, as usual I'm going to take T flip-flop for my work. Now I'm going to make the step number 5, that is excitation table. That means the required input for the T0 flip-flop, T1 flip-flop and T2 flip-flop. Now we'll make required input for this transition. If you look at here, first one 0 to 1, 1, 1 to 0, 1, 0 to 1, 1, 1 to 0, 1, 0 to 1, 1, 1 to 0 means 1, 0 to 0 means 0, 1 to 0 means 1. Now similarly, if you look at the second one, 0 to 0 means 0, 0 to 1 means 1, 1 to 1 means 0, then 1 to 0 means 1, 0 to 0 means 0, 0 to 0 means 0, 1 to 0 means 1, 1 to 0 1, 1 to 0 means 1. Take the last one, 4 zeros, 3, 0 to 0, 0 to 0, 0 to 0, that means 3 zeros. Then 0 to 1 means 1, and 1 to 1 means 0, 1 to 0, 1 to 0, 1 to 0, that means 1, 1, 1. Now you got the required input for the T0, T1 and T2. Now we are going to make the K map for each T flip-flop. This is my Q2 bar and Q2, Q1 into Q0 bar. Now if you fill the T 1 1 1 1, then 1 1 0 1 1 1 0 1, this is for T0. I will make for T1, it will be 0 1 0 1, then 0 0 1 and 1. Similarly, if you make it for T2, zero, zero, 0, 1, 0, 1, 1, 1. So now we got the all the three K maps. We need to form the K maps and to get the T0 expression, T1 expression and T2 expression. So we can form one quad here and one more quad here and one more quad here. So you are going to get total 3. So in this case I am going to write as Q2 bar plus, for this quad you are going to get it as Q1 bar, and this quad I am going to get it as Q0. So similarly for T1, so you are going to form one pair here and one more pair here. You are going to get T1 as, if you make this as a pair, in this case it will be Q2 bar times Q0. In this case Q2 times Q1. Similarly, if you take for T2, so you can form 3 pairs, one here and one here. So your T2 will be, so in this case Q1 into Q0 plus, in this case, Q2 into Q1, and in this case Q2 into Q0. So these are the input for the each flip-flop. Now we are supposed to design this by using DID software. We'll try to verify whether this is going to work or not. Now let us simulate the same circuit. So whatever the expression we derived for a T0 input, T1 input and T2 input. If you look at here, your T0 is connected to Q1 bar, Q2 bar and Q0 as we derived earlier. And similarly, if you look at your T2 input, look at this T2 input. T2 input connected as Q0, Q1, Q1, Q2 and Q2 and Q0. And similarly here T1 also. If you run this circuit simulation, we are going to count only 0 to 5. Let's run the simulation. Now you can clearly see after 5 it goes to 0 state. So this is how we can systematically design the modulus counter. This can be extended to any other modulus by designing different circuits for the T0, T1 and T2. That's all for today's lecture. Thank you all.